Alright, so we're going to hit the key ideas from our Unit 2, Day 5. We're talking about the fundamental theorem of algebra and looking again at factoring complex, or using complex numbers to factor irreducible polynomials. So, key theorem that we're going to need to know is that complex roots will always occur in conjugate pairs. So if you know that 2 plus 4i is a solution, you also know that 2 minus 4i is a solution. So if you think of these as solutions, we have 2 plus 4i. Well, imagine if we got all of our terms on one side of the equal sign. Well, I could subtract 2 and subtract 4i from both sides, and I would end up with x minus 2 minus 4i. And I could do the same thing with my other solution, which is 2 minus 4i, its conjugate pair. If that is equal to x, then I'm going to end up with x minus 2 plus 4i, which is going to be my second factor. And if I wanted to, I could multiply this factor by this factor and get an irreducible quadratic function, which we'll see later. So a really important consequence of the fundamental theorem of algebra is this, the linear factorization theorem. Basically what it says is that you can factor every single polynomial completely, and whatever the degree of your polynomial is, that's how many linear factors you will have. And you can always just write those factors as x minus whatever the solution is. So let's jump to the big picture now and see what we can do with this. We want to find all of the zeros of this function, and maybe we even want to factor it. So we are told that 1 plus 3i is a 0, so that means that 1 minus 3i is also a 0 because they always occur in conjugate pairs. So I can write those as two factors, x minus 1 plus 3i and x minus 1 minus 3i. And now I want to multiply these two together and see what I get, because I'm going to get an irreducible quadratic. So if you multiply all this together, look at what happens. You have an x squared, you have 1 minus x and another minus x to give us minus 2x. We have a negative 3xi right here, which is going to cancel with a positive 3xi. We have a negative 3i, which is going to cancel with a positive 3i. And then look at our last square. It really was negative 9i squared, but I squared is the same as negative 1. So it's like negative 9 times negative 1 gives us a positive 9, and we had a positive 1 as well. So we get x squared minus 2x plus 10. Cool. Now, at this point, a lot of people in class tried to then factor it using real numbers like x minus 5 and x plus 2 or something like that. That's obviously not it, but the point is you won't ever be able to find anything that is it, because the only way to factor this quadratic function is with what we started with, factoring using complex numbers. So again, this is just going to correlate to some quadratic function that doesn't have any real x-intercepts, because if a polynomial function has a real x-intercept, it will have a real factor and real solutions. But this quadratic right here only has these two imaginary solutions. So what can we do with this? Well, we know those are factors because we're told they're solutions, and we know that they are equivalent to that polynomial, x squared minus 2x plus 10, that quadratic function. So I can take that value, let's see if I can write it, x squared minus 2x plus 10, and I can divide my original polynomial by that. And when I do this polynomial long division, I'm going to end up with a new quadratic function, and maybe I can factor it and find real zeros. So let's do some long division. X squared goes into x to the fourth, x squared times, so I'm going to get an x squared term. X squared times x squared is x to the fourth. X squared times negative 2x is negative 2x cubed. X squared times 10 is a positive 10x squared. So now I'm going to go through, I'm going to subtract the whole thing. X to the fourth minus x to the fourth, they cancel out. negative 3x cubed minus negative is like a positive there. So negative 3 plus 2 gives me a negative x cubed. 6x squared minus 10x squared is going to give me a negative 4x squared. Now drop that 2x down and play the game again. X squared times negative x will give you negative x cubed. So I'm going to get a negative x term up here in my quotient. And negative x times x squared is negative x cubed. Negative x times negative 2x is a positive 2x squared. And negative x times 10 is a negative 10x. And now again, we're going to subtract that whole thing. So those terms are going to eliminate. I'm going to get negative 4x squared minus 2x squared is negative 6x squared. I'm going to get 2x minus negative 10x is a positive 12x. And I'm going to pull that negative 60 down and play the game one more time. Well, x squared into negative 6x squared is going to give me negative 6. Negative 6 times x squared is negative 6x squared. Negative 6 times negative 2x is positive 12x. And negative 6 times 10 is negative 60. So you notice that's exactly the same. So when I subtract it, I will get no remainder, which tells me that x squared minus x minus 6 is a factor of this polynomial. So I know that this is going to factor as, sorry about that. It's going to factor as x minus 1 plus 3i times x minus 1 minus 3i times, now I'm going to factor that answer there, what I got, that x squared minus x minus 6. Well, that's going to factor as x minus 3, x plus 2. So those are my additional two factors, x minus 3 and x plus 2. So then I know that all of my zeros are going to occur when x is the original 2 I found, 1 plus 3i, 1 minus 3i. And now I also know that since this is equal to our f of x function, I will also have zeros when x is positive 3 and x is negative 2. So these would be all of my zeros, and this would be that function completely factored using complex numbers.